Okay, so this is the 2016 complex numbers question. And we're going to go through it looking at what was done right here and what was, I suppose, incorrectly assumed. So the first thing I'm going to do is I'm going to write down that we were told that 1 plus I is a root or a solution to the quadratic z squared plus minus 2 plus I times z plus 3 minus I equals 0. So 1 plus I is a root of this. Now, if the quadratic equation has coefficients that are all real, so a quadratic in the form az squared plus bz plus c equals 0, and if a, b, and c are all real numbers, well then the roots occur in conjugate pairs, meaning that 1 plus I would be a root and 1 minus I would be the other root. Now that's not the case in this question because we can see that the coefficient of z has an I in it. And if it has an I in it, that rule about the roots being conjugate pairs, that goes out the window. So let's proceed knowing that. The second thing to look at is, well, I kind of like what was tried up here. This answers a different question. This answers the question that says, show that 1 plus I is a root. So how does it answer that question? Well, if you sub 1 plus I in for z, so 1 plus I squared plus minus 2 plus I times 1 plus I plus 3 minus I, well, this work here is all correct, and you end up with minus 2 minus 1 plus 3, which is minus 3 plus 3, which is 0. And when you sub in a root into a quadratic equation, you should get 0 if it's a root. So this here showed that it's a root because everything ends up cancelling and you get 0 equals 0. But it doesn't help us find the other root, which we're calling m plus ni. So how will we go about finding this other root? Well, let's see what was done next, because again, I don't mind this, there's a lot of this that is right. If you want to form a quadratic equation, what you do is you use this formula, z squared minus the sum of the roots times z plus the product of the roots. Now, and we say that it's equal to 0. So here we have a mistake just with the plus, that should be a minus. But then underneath that there's just some incorrect work. I'm not sure where we're getting the 1 plus 3i. We can't use this at the minute in this way to form an equation and get what we have up here originally. So how can we use this? Well, we can do it like this. We can underneath write down our quadratic. Our quadratic is z squared. Now we have a plus. I'm going to change it to a minus by changing what's inside the bracket. We have minus 2 plus I, but if I put a minus outside the bracket, I can say plus 2 minus I times z, and then I have my plus 3 minus I. Now remember, our roots are as follows. The one that we were given, 1 plus I, and then the other root is in the form m plus ni, or we could call it a plus bi, or we could call it x plus yi. It doesn't really matter what we call it. They've given it m plus ni. Well, if we break it down then, well, what we can see is, if we take this part of it here, well, this here is the sum of the roots. This 2 minus I is the sum of the roots, and here's our two roots, 1 plus I and m plus ni. So I'm going to write down that, and we'll do it in green, 1 plus I, our first root, plus m plus ni, our second root, that's equal to 2 minus I. Now, this is called a complex numbers identity, so we're not going to bring things from one side to the other. What we're going to do is we are going to let the real numbers on the left equal the real numbers on the right, and the imaginary numbers on the left equal the imaginary numbers on the right. So let's go ahead and do that. So the real numbers, first of all, on the left hand side, well, we have 1 plus m. So 1 plus m is equal to the real number on the right hand side, which is 2. Well, we can see that m is equal to 2 minus 1, which is 1. Okay, now how do we find n? Well, the imaginary numbers on the left So I plus ni, they're equal to the imaginary numbers on the right, which is minus I. Divide across by I, so I have 1 plus n equals minus 1, and I have n equals, bring this one over the other side to make it a minus 2. And this is the answer to our question. It's as simple as that. And it comes from this formula which was known, just with a little mistake, but just by forming it like this, we can figure out that m is 1 and n is minus 2. So the second root of this equation, the first root is 1 plus I, and the second root is m, 1, and then minus 2i. They're the two roots of this quadratic equation. So root 1 and root 2. Now, well, what about the product of the roots? Could we have done it with the product? Well, we could have, we don't need to because we already have the solution, but let's just go ahead and see that we get the same answer, and then we'll have a look at one more solution. So we're saying the product of the roots is 3 minus I. So going back to the idea that the two roots are 1 plus I and m plus ni, well then the product, 1 plus I multiplied by m plus ni, that would be equal to 3 minus I. So let's multiply it out. So 1 by m is m, 1 by ni is ni, I by m is mi, and then I by ni is ni squared, and that's equal to 3 minus I. This plus ni squared, well, I squared is minus 1, so plus n by minus 1 is minus n, so the real numbers are m plus n, and then the imaginary numbers are plus ni plus mi, and that's equal to 3 minus I. So we have m, now plus n times I squared is plus n times minus 1, which is minus n, so I'm going to write that next. And then I have plus mi plus ni, and that's equal to 3 minus I. And so as before, I'm going to form two equations. I'm going to form a real equation and an imaginary equation. So the real equation is m minus n is equal to 3. So the left-hand real numbers are equal to the right-hand real numbers. And then the imaginary equation is mi plus ni is equal to minus I. Divide across by I, we get m plus n is equal to minus 1. So we have a simultaneous equation here. We have equation A and equation B. I'm going to add those. So equation A, first of all, is m minus n equals 3. Equation B is m plus n equals minus 1. So I'm going to sum those two equations. The n's cancel. I get 2m is equal to 2. M equals 1, as we found out in the previous example. And then sub m equals 1 back into either equation, so we'll sub it back into equation B. So we have 1 plus n equals minus 1, n equals minus 2. And again, that was something we already knew from doing the sum of the roots. Okay, so look, that's one way to approach the question, this idea of having an equation z squared minus the sum of the roots z plus the product of the roots. We're going to look at the second way we could do this equation. So we'll just come back up here and we'll move across here. Let's start with this equation. And what we're going to do is we're actually going to do the minus b formula. Now the minus b formula, what will happen is we'll confirm one of the solutions. So we're going to use the minus b formula. We'll get two solutions. One of the solutions is the 1 plus I that we found previously. And the other solution should be 1 minus 2i, which the reason we know that is because we've done it in a previous method just a second ago. So let's do the minus b formula. So the minus b formula is minus b plus or minus the square root of b squared minus 4ac all over 2 times a. So what's a, b, and c? Well, a is the coefficient of z squared, which is 1. B is the coefficient of z, which is minus 2 plus I. And c is the constant, which is 3 minus I. So not like our usual quadratic equations where we have one term in each of the a, b's, and c's. Here we have a couple of things, a real and imaginary part and the b and c part, but they can still go into the formula and we'll see it works out okay. So minus b, well that's going to be minus bracket minus 2 plus I. Plus or minus the square root of b is going to be minus 2 plus I squared minus 4 by a, which is 1, by c, which is 3 minus I, all over 2 times a, so 2 times 1. Now tidy it up, so it's minus minus 2, which is 2 minus I, plus or minus the square root of, now square in a bracket, we're going to square the first, 4, square the last, which is plus I squared, and then twice the product, which is minus 4I. And then we have minus 4 by 1 by 3, which is minus 12, and we have minus 4 by 1 by minus I, which is plus 4I. That's all over 2 by 1, which is just 2. So taking it down another level, we have 2 minus I, plus or minus, now let's tidy up what's inside the square root here. So we have 4 minus 12, let's say, is minus 8, first of all. And then we have minus 4I plus 4I, which gives us 0. And then we have plus I squared. Now plus I squared is plus minus 1. And then that's all over 2. Now that's 2 minus I plus or minus the root of, well, minus 8 minus 1 is minus 9, all over 2. And this is where we get to an issue that if this was an algebraic equation outside of complex numbers, we would have an error here. We can't have the square root of a negative number. But in complex numbers, we have the idea that I is the square root of minus 1. We can change root minus 9 into root 9 times root minus 1. The root of 9 is 3, and the root minus 1 obviously we're calling I. So we can change root minus 9 into 3i for the purpose of this equation. So it's 2 minus I plus or minus 3i over 2. And at this stage we have to split it up into two parts. So we have, the first part is 2 minus I plus 3i over 2. And the second part is going to be 2 minus I minus 3i over 2. So 2 minus I plus 3i is 2 plus 2i over 2. 2 plus 2i over 2, which is 1 plus I. That was the root that was given to us initially in the equation. And then the second one is 2 minus 4i over 2, which is 1 minus 2i, which was the second root that we discovered using our previous method.